Hi everyone, welcome to AP Daily. My name is Tim Gallagher. I'm an AP Computer Science teacher from Winter Springs High School, located just outside of beautiful Orlando, Florida. Today we are going to discuss topic 3.6, which is equivalent Boolean expressions. And in this first of two videos, we are going to introduce DeMorgans laws and talk about how they can be applied to Boolean expressions. So what will we learn? Well, we are going to compare and contrast equivalent Boolean expressions, and we're going to use DeMorgans Law to do that. And we'll see how these equivalent Boolean expressions will evaluate to the same value in all cases. So before we get started with that, who was De Morgan and what are his laws? Well, Augustus De Morgan was a 19th century British mathematician whose laws or rules about Boolean logic allow us to simplify expressions when they're negated. We're going to use our logical operators, the and, the double ampersand, the or, our double bar, and not, the exclamation point, with our compound Boolean expressions to demonstrate how these laws are applied. So let's look at an example. Here's what De Morgan's laws say. If I have two Boolean variables, or they could be Boolean expressions, but for right now, let's just talk about variables, A and B. So if I have A and B, and I have a not symbol on the outside of that, De Morgan's laws say that that is equivalent to saying not A or not B. Basically, what the laws say is that if you distribute the not to the A and to the B, you can flip the and to an or, and you have equivalent expressions. We're saying that when we distribute the not to each term of this compound Boolean expression, not A and B becomes not A or not B. And these are equivalent no matter what A and B happen to be. The same is true if we have an or expression. So if we have not A or B, that's going to be equivalent to not A and not B. Again, we're distributing the not to the A and the B both, and then when we do that, the or symbol has to flip to the and symbol. So when we distribute the not to each term of our compound Boolean expression, not A or B becomes not A and not B. And that's basically what De Morgan's laws state. Before we go any further though, I do want to focus on not here just for a moment. So we know that if we have a Boolean variable A, not A is equivalent to, well, not A, right? Not true is false and not false is true. But what about for Boolean expressions? We want to distribute that not symbol. So for instance, if I have this expression x greater than 0, which is either true or false, right? But what if I negate that? What do I get? So I want to say not x greater than 0. Well, if you think about it, not x greater than 0, isn't that the same as just saying x not greater than 0? And what does not greater than 0 mean? Well, isn't that equivalent to x being less than or equal to 0? Because less than or equal to is the same as not greater than. And this works for all of our relational operators. When you distribute a not with a Boolean expression, it flips the relational operator to the opposite relational operator. So for instance, this works for all of them. If I say not x less than 0, that's the same as saying, well, evaluate x greater than or equal to 0. Not x greater than or equal to 0, that's equivalent to evaluating x less than 0. Not x less than or equal to 0, that's equivalent to x greater than 0. And all of those work. When you distribute the not, it flips to the opposite relational operator. And it even works with these two as well, where I say not x double equal sign 0. So I'm basically saying not x equals 0. Isn't that the same as saying not equal to 0? X not equal to 0. That's the same as not x equals 0. And then finally, on this last one, not x not equal to 0 is the same as saying is x not equal to 0. Not equal to 0, a double negative, that's just the same as saying is x equal to 0 using the double equal sign. And that's how the not symbol works with all of our relational operators. So let's put it all together. Here's a common mathematical expression. You may have solved in math an inequality and come up with a solution, something like this, where x is less than -5 or x is greater than 10. And here it is graphed on a number line, right? So less than -5, it goes to the left, and greater than 10, it goes to the right. Open circles because it's not less than or equal to or greater than or equal to. And here's how we'd write that expression in Java. We would say x less than -5 or x greater than 10. It's not and, because it has to be one or the other, because it's two different parts of my number line. But what would happen if I'm looking to negate the expression? Basically, what is the opposite of x less than -5 or x greater than 10? If you look at the number line, it's this portion right here. I want all of the stuff inside the two blue arrows that I currently have. How do I do that? Well, I'm going to negate it. So when I negate it, can I use DeMorgans Law? Sure. So here is not x less than 5, x less than -5, or x greater than 10. What happens using DeMorgans Law? I distribute the negative, or distribute the not, and I flip the or to an and. So not x less than -5 and not x greater than 10. Now what happens? Well, when I distribute the nots to each one of these, this becomes x greater than or equal to -5 and x less than or equal to 10. So when I distributed the not, the less than became greater than or equal to, and the greater than became less than or equal to. So these are equivalent expressions. When I negated my original expression and I applied DeMorgans Law, I could say x is greater than or equal to -5 and x is less than 10. And if you think about that, that covers all of the area that's currently not shaded inside of my number line. And that's how DeMorgans Laws work. So what should we take away? Well, we've been comparing and contrasting equivalent Boolean expressions, primarily using DeMorgans Laws, and we saw that equivalent Boolean expressions will evaluate to the same value in all cases. But we didn't really look at all cases. Can we prove that this is true every single time? We can. We're going to use something called truth tables, and that's what we're going to cover in the next video. So thank you so much for joining us at AP Daily today, and we'll see you next time. Take care.